Welcome to this lesson on Gaussian elimination and complexity. So linear algebra takes off from a question of just trying to solve systems of linear equations. I've written down a set of linear equations for you here, and in case it's helpful, you can remember that it's also possible to write these in kind of matrix vector format, where you have a matrix 2, 4, minus 2, 1, 4, minus 3, -2, -6, 7 in this example, times the vector of known unknowns, x1, x2, x3, and this is equal to the right-hand side, 8, 8, minus 3. More generally, we might write this as ax equals b. And there's two ways to think about this system of equations. One way is when you remember that matrix multiplication by a vector, like this, means taking a linear combination of the columns. You see that the problem is this one that I've boxed here. It says how much of this first column vector plus how much of the second column vector plus how much of this third column vector do I need to arrive at the location in 3 space 8, 8, minus 3. So that's, can we get to the right-hand side as a linear combination of the column vectors. The other way to think about this is just to focus on this original form of the equations, and remember that each equation describes a plane, and you can ask if those planes intersect, and if so, how many intersections there are. And quick reminder from linear algebra, the answers are that there's 0 points in the intersection, potentially 1 point in the intersection, or infinity points in the intersection. Those are the only options. And you can see pictures like this. This example, there's 0 solutions. This example, there's 0 solutions. This example, there's 0 solutions. Here, in this one, there's one solution. There's this 1 point right in the middle where all the planes intersect. Here, the planes intersect in a line, this line, so there's an infinite number of solutions. There might be other arrangements of the planes too, but it's always 0, 1, or infinity. So to remind you of some things from linear algebra, the identity matrix is just the n by n matrix with 1s along the diagonal here. And then there's this thing we call the inverse of a matrix, and the inverse of a matrix, written as A minus 1, satisfies A times the inverse equals the identity. All right, so a naive thing you might try to do is that if you had to solve ax equals b, you could think, oh, let me calculate the inverse of a. So first calculate this, then left multiply by it, so that the a inverse a term goes away, and you're left with x equals a inverse b. And mathematically that works, but computationally, especially for large systems, it turns out to be really impractical. Calculating the matrix of the inverse of a matrix has a lot of things that can go wrong or be computationally costly. Let's remember another method for solving systems of equations, this thing called Gaussian elimination, right? Where you try to convert ax equals b to the form ux equals c, where u is an upper triangular matrix. And so we can talk about the complexity of this, and we won't derive the complexity results here, but to do that conversion into this echelon form, it turns out you need order n cubed multiplications, divisions, and order n cubed additions and subtractions, where n is the width and height of your square matrix. And then once it's in that form, you still have to be able to solve for x. And that step is called back substitution, and it turns out that that has order n squared multiplications and divisions, and order n squared additions and subtractions. And why do we care about the complexity of these methods? It's because the more complex it is, the longer it's going to take, and the worse it gets as you increase n. So this has to do with predicting computation times. How long is your algorithm going to take? It's good for comparing algorithms, right? If one algorithm is n squared and the other's n cubed, one of those things requires fewer operations. And if your code is running slowly for some problem that you're solving, thinking about the complexity can help you identify bottlenecks in your code. Which part of your code is making things take so long? And in general, when we're thinking about a whole bunch of different methods for solving ax equals b, here are things you need to keep in mind. There's the computational complexity that we've been talking about. There's memory required on the computer to do it. There's convergence, meaning if your method is an iterative method, like how many iterations does it take to converge to what is the order of convergence? And are you guaranteed convergence or not? And then there's something you'll learn more about later called conditioning, which has to do with error magnification. Some other things to keep in mind are, does your matrix A in your ax equals b problem have any special structure? A lot of problems have special structure. The matrix might be sparse, which means most entries are 0. Or it might be banded, meaning there are sort of patterns that go along diagonals. There's a property called diagonally dominant. There's a property called symmetric positive semi-definite. Don't worry if you don't know what all these mean right now. But depending on the structure of A, some algorithms might be more appropriate, faster, and so forth. Another consideration is if you're solving ax equals b once, or if you have to do it over and over in some application. If you're just doing it once, maybe you don't mind a high complexity algorithm so much. If you're doing it lots of times, you might care more. Also, whether or not you start out having an estimate of the solution might affect your choice of method, and the desired level of sort of precision that you need in your final answer. What's your tolerance for error in X? These are all, this is a lot to keep in your head right now, I know, but these are all things that one can and should think about when choosing a method. And as we see different methods, we'll revisit some of these ideas. I'm going to end by just kind of quickly running through what I like to call the big linear algebra theorem, which says that the following statements are all equivalent about an n by n matrix A. A is non-singular, where non-singular for us is just going to mean any of these remaining things are true. Okay, so the things that make a matrix non-singular are it's invertible, meaning it has an inverse. Equivalently, its determinant is not 0. Equivalently, it does not have an eigenvalue of 0. Equivalently, the only vector for which AZ equals 0 is the 0 vector. Equivalently, the null space of A is 0. Equivalently, the columns of the matrix are linearly independent. Equivalently, those columns span the space you're in, Rn. Equivalently, the image of the matrix is Rn. And equivalently, there's a single solution, a unique solution, Ax equals b, no matter what b you choose, so not 0 or infinity. And finally, equivalently, if you do Gaussian elimination, if you do row reduction, you can reduce A to the identity matrix. That was like a really quick review of a lot of linear algebra, and I think it's a good exercise, not to prove these to yourself, but to at least make sure you understand what each one is saying, and that might involve reminding yourself about some vocabulary from linear algebra as well. Okay, thanks for listening.